Okay, I will present the exoplanet working group, which is led by me and Yossi. So first of all, review of several of the science cases. So I'm starting with what I think and what we think is the leading cases. So probably the main one is activity and habitability. We know that UV flares has a lot of effects on atmosphere evolution and on the habitability of a planet. This is relatively not very well probed at the moment, especially not for a large sample, and we will be able to control the depth. In addition, given that we are in the UV band, the study of atmospheres, comparative transit depths, if we know that there's an exoplanet in our field, we can compare the visible transit depth to the NUV one, and that will allow us to get some information regarding escaping atmospheres and so on. And the stellar planet interaction, which Svi will talk right after me. As far as transit detection, there's main sequence transits, cool stars, FGK dwarf transits, which Oded and David will talk about in a couple of minutes. And there's the OBA main sequence, maybe hard dwarfs. There are some cases for post-main sequence, FGK giants, chromosphere or corona occultation, which are expected to be hotter than brighter in the UV. And the white dwarf transits, which is probably the most interesting case as far as transit detection at the moment. And also the case for detection of transit timing variations, which already are not talking about, which is going to be maybe their work. Yes, Barak, let's see.
What is the requirement for photometric precision? I think
so. I will go over that and we will see exactly the various cases. Of course, there is the case that we raised at the beginning regarding Redlick and so on and so forth. In this discussion, I'm going to assume that this is not a problem. Of course, there are various cases that we can try and solve it or improve the situation that we have at the moment. One of them, for example, is probably a continuous follow-up of the same targets in the visible from the ground. Me and Iran as a project that we are developing in an effort to try and do that. The large array observing telescope we are working on, and that can be one such project that will support this effort. So field content, one of the things that we need to take into account is that overall for every object within the 3 years lifetime, we are going to have 130,000 samples or so, and that's including all the corrections needed for the availability and the 90% due cycle and so on. So we are going to have a very good sample of whatever it is that we are observing within the continuous field of views that we are examining. So I took one such field. I examined the 200 square degrees field center at RA 210 and declination 60. Not exactly what we talked about before, just because Galaxy is not really completed that field because of bright sources in the field that we were discussing. I examined the all imaging sky catalog, which is completed 22nd magnitude, and we have identified 67,297 targets within that field. Most of them as SDSS cross-match, and around 45,000 are classified in the SDSS as stars. We have 43,000 identified in the Gaia cross-match, with a Gaia cross-match, and with abscess fit, which are fits that gives us a main sequence star characteristics like temperature, radius, and so on, the order of 40,000. This needs to be corrected for the filling factor from the galaxy sky, which is roughly 76%, again, because of bright targets. Activity and habitability, stellar activity and its effect on planetary atmosphere. We know that strong activity of the host star can have large impact on the exoplanet atmosphere evolution. Ultrasat is going to give us unprecedented data in time domain wavelengths, both in the frequency of exposure and the fact that we are going to observe in the UV band, and therefore we will be able to really determine NUV flare frequency and luminosity distribution for host stars as a function of spectral subclasses, rotation period, and so on. Just to give the current best study of these events is the master survey. It's an HST legacy survey by Franz et al. And it's a nice spectrum from this survey by Lloyd et al. And there is indication there that there's no clear correlation between the NUV flare or the NUV activity and the activity in, for example, calcium-2, H and K, which is the strongest activity that we can observe visible. And therefore, there is a lot of merit to going and observing at that given wavelength. And that will be very, very interesting. And we will basically be the only game in town for that thing. So, yes?
What do you mean by activity in calcium-2?
Calcium-2, H and K is the best indicator in the visible band that currently is being used for as an activity indicator in a star, right?
Emission lines.
Emission line.
Oh, an emission line?
Yeah. And there is, in comparison, in simultaneous HST cross observation, spectroscopic in the UV, there's no clear correlation between the calcium H and K emission line flux level and the NUV emission.
During the flare?
During the flare. So the correlation is suggestive at best. And therefore that will be a the fact that we can probe at the band that we are interested, at the NUV, which has more effect on the exoplanet atmosphere evolution, makes us really, really at a unique point in that regime. Okay? I would like to focus on MVOF, and again, I'm putting aside the red leak. If you ignore it for long enough, it might not be a problem, but
you can join the government.
Huh?
You can join the government.
Yeah. MVOFs are the ideal host for exoplanet candidate for transmission spectroscopy studies. That's because of the small radius comparative to FGK9 sequence. We are going to have thousands of MVOFs in our field of view, observable, at least as far as the NUV emission. There's a very interesting case about our specific band, the NUV band between 220 and 280, is that it's not only a stress or something that can bring an exoplanet atmosphere and strip it. It's actually also a boost stressor, which is one of the leading theories right now for supplying the energy for prebiotic molecule generation in the early Earth. There seems to be in M12 some lack of that kind of emission, of the UV emission at the NUV band. There's a lot of effort now going on into understanding this problem by the group of Saselov at Harvard and Ranjan in MIT now. And therefore, we will also be able to really target that specific case and identify whether interesting candidates for very expensive studies, follow-up studies and search for biomarkers, identify for those the leading candidates in terms of the UV emission, kind of study the UV habitable zone, so to speak. I just want to give a self-advertisement that one of the leading instrument that is being now developed for spectroscopic biomarker searches. The Institute is a major partner with it through the GCLEF collaboration, and we are going to build a fiber link that will connect that instrument to the telescope here at the Institute. So that's my self-advertisement. As far as white dwarf transits, I think it's the most interesting case at the moment in everything we have. From the Gaia white dwarf catalog at the field of view of 200 square degrees, we identify of the order of 200 white dwarfs. The completion level to 250 parsec or so is 44% or so, so we're talking about 460 white dwarfs. I found 100 cross matches with within the Galax catalog. Overall, between the two fields that we observe and the fact that we will be able to observe, hotter white dwarfs than, for example, Gaia. We expect 400 white dwarfs above limiting magnitude in a single field of view. We need to take into account that as far as transits go, in case of white dwarfs, we are not looking at an accuracy of sub-percent. The occultation depth or the transit depth is order of tens of percent, not a complete obscuration of the target, and therefore that's kind of ideal for us, where we are not really targeting the standard transit precision that is offered by Kepler or TESS. This is, for example, calculation of the signal to noise in a single image for the white dwarfs that I found in this field. You can see here the number of white dwarfs as a function of the color between what I identified in Galaxy and what you can find in the Gaia catalog. Of course, you can see the bluer ones, big surprise. And overall, we will have enough signal to noise to really identify small occultations, even to the order of a moon that you can see in the map. So everything that is right of that line, we can actually even identify or detect a transit when a moon-sized object is going in front of the white dwarfs, and that will definitely be an interesting case. And one of the things that this is really interesting is the current limit right now that we have, the best current limit is from the K2 mission. It's written here that it's of the order of 1,200 white dwarfs, but it's actually false. It's 1,200 white dwarfs in all the survey, but when you actually go into and find out what is the number of white dwarfs that they actually observed at high cadence, in order to get those limits, the number is 300. So overall, maybe we are not going to beat it by far, but we are comparable to currently the best results there are, and therefore our impact will be much, much bigger than in other cases. So that's, I think, the best case for us to have a large impact in terms of transit studies. Other exotic transits.
But this is assuming only two fields, right?
This is assuming only two fields. Of course, that if we go to more fields, then the number of white dwarfs is going higher. On the other hand, we need to take into account that usually transits of white dwarfs is of the order of a minute to 2 minutes to 3 minutes, depending on what is the orbit. If we are talking about a critical zone, we are talking about 2 minutes transit, so there's a limitation.
The transit itself.
Huh?
Half a minute,
One data point.
even half a minute.
But then it repeats every.
Yeah, it repeats enough 6 hours to 24 hours in the critical zone.
That's again another motivation to go to more fields, as you said.
Yeah.
Because if you looked at the field for a few days, that's it.
You can move to the other field.
Yeah, you won't see it. If there's no transits there, then you won't see it.
So we should probably talk also about the different one.
And I should also say that just your probability of seeing a transit of a planet around a white dwarf, in the nearest orbit that can survive tidal disruption
is much.
is like 1 out of 500 or something like
Yes.
that. Okay, so in even if all white dwarfs had planets, your chances of seeing it with a survey like this are still small.
So I want to.
So you really, if you can, you really want to go to samples of many thousands.
So I actually put that in the next example. All the estimates of transits that we have are consistent with 0, unfortunately. This is not an exoplanet application. We still have some cases that will be interesting. Here it will be interesting also because we will also investigate a very different population of white dwarfs than, for example, what you saw in Kepler. We will actually be observing the hot ones or the hotter ones, while Kepler will bend mainly in the R, G and R. So there are cases, of course, I'm not claiming that we will have 10 exoplanets in any case, so maybe some FGK hot Jupiters, but then a Vivisha, but those are diminishing contribution, I should say. Other exotic transits, as far as hot dwarfs OBA, I identify of the order of 100 stars within our field of view. If I'm comparing that to population, it's roughly 200 per field of view. Again, the signal to noise is not very, very high, but still there are several cases that we can achieve a sub-percent precision, so maybe not necessarily exoplanets, but red dwarfs, brown dwarfs specifically, yeah. Yes, because overall, the number of candidates that we have for exoplanets around the OBA stars is 22. So every one here counts. Or every one is an addition. If we have 2 or 3, then okay, we already contributed to the current sample. Red giants, again, here the chances are very, very low. There is the suggestion that Asif, Gaudi, and Stanek about limb augmentation or a limb transit in which the limb is hotter than the disk itself, and therefore you'll have a deeper transit. At the moment, there's one case that I think is very questionable for observing this phenomena, but well, we will have the data, so we will definitely investigate that, and we'll give it to you once I think it's sequence stars.